So what I will do in the rest of this lecture is we'll actually look at what sampling does to complex exponentials or sinusoids. And I'll flip between those two terms. They're basically the same thing, okay? The one is just rotating, like this is the complex exponential. It's doing that thing, rotating, and sinusoids are just pulsing. We'll have an in-depth look of what happens when we sample these signals and what happens with basically continuous frequency and how that maps to discrete time frequency. Okay, so let's start with stuff that you've learned already. Here we've got a continuous signal. I'm writing the complex exponential, but you can also think of it as just like a cosine wave. It rotates or pulses at some frequency f0, okay? And I can also write that out in terms of its angular frequency. Quickly, what's the unit of f0? Hertz. And give me the other name for hertz. Cycles per second, or I'll just write it out as continuous, which I can't spell, continuous cycles per second, okay? And so what that means is if this is my complex exponential and we're just looking at the cosine component of it, then it means that if f0 is 1, it means that within 1 second I've done 1 cycle, okay? If f0 is 2, then it means that within 1 second I'll do 2 cycles. Okay, cool. I can also define it in terms of angular frequency, and that's pretty easy. 1 cycle is equal to 2 pi radians. Big omega 0 is just equal to 2 pi f0. And then we have this omega 0, which has units in radians per second. Now, forget about continuous stuff. Let's say we've got a discrete signal now. It's also a complex exponential. And we are going to sample, well, that signal has already been sampled. We have some samples for it. So we've got x0, x1, so this is x block 1, x2, x3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now I messed up. Can only count in English up to some number. Okay. That's a sampled signal. Here we've got ej2 pi, and then we have it in terms of n. This should not be t, that should be n. Okay, so this is a signal in terms of, this is x block 1, x block 2, and so on. Okay, I just sampled a complex exponential. For this thing to be a sampled version of this thing, we need one equation to hold. xn, block n, should be equal to xn at my sampling frequency. Basically what I'm saying is, for these two sides, for this side and this side to match up, this point here should match up with the point happening at t. The second point here should match up with 2t. The third point here should match up with what happens at 3t, and so on. Okay, and if this is true, then these dots are sampled versions of that thing. Okay. And what we will do now is we'll quickly look at the equation here and the equation here and see what happens if this is true. Okay. So if those two things are true, then ej 2 pi f omega 0 n, so that's my discrete time frequency, is going to be equal to this thing here. Okay. ej 2 pi f 0 and then nt, that's right, boom, okay. So for those two things to be equal, it means that 2 pi f omega 0, this is my discrete time frequency n, should be equal to 2 pi f0, that's my continuous cycles per second frequency, times n times t. Okay, now if I cancel these things out, tunk, 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 tunk. Okay, what I end up with is that f omega 0 should be equal to f0 times t. I can write that in a different way. That's equal to f0 over fs. What is f0's units? You've already written it down. It's continuous cycles per sample, per second. So this is cycles per second. Okay, what is the units of fs? It's samples per second. second. So what is the units of f omega 0? Cycles per sample, spot on. Cycles per sample. Okay, and this should not be surprising at all. You should have kind of expected this if you paid attention in the previous lecture when we derived the discrete time Fourier transform, because I'm going to go back a few slides. Along the way in the discrete time Fourier transform, we defined this f omega thing, and we defined it as f times t, which is this, and we figured out that the units are cycles per sample. What we've done now is we basically said, if I have a continuous exponential function and I sample it, and it needs to look like this, then for this thing to be a sampled version of this thing, I need this to hold. So f omega 0, let's just write out the units completely. It's continuous cycles per sample. You can also have a discrete time angular frequency. So you can have omega 0, which is actually there, which is just 2 pi f omega 0. And the units for omega 0, that will be in radians per sample. And the important thing is, well, there's actually no time information in these units. Let's just take together what the DTFT gives us and what it tells us about sinusoids. So here I've got a cosine signal, continuous cosine signal, x of f. The spectrum of a continuous cosine has an impulse at minus f0 and an impulse at f0. I will now sample this signal. I will get its discrete time Fourier transform. So I will go from this to this, discrete time Fourier transform. So f omega, just as a recap from the previous slide, is equal to f over fs. This equation is what guides what happens on this slide. Okay, so if this is my continuous cosine function, my sampled spectrum is going to look like this. And I'll just do it quickly. I'll have an impulse, and I will have an impulse. And that impulse will sit where? Not at f0, but at f0 over fs, if this axis is in terms of f omega, which it is. This one will sit at minus f0 over fs. Okay, it's crazy. I took my continuous spectrum and I sampled it, and I just know the answer. The answer isn't complete, but I'm almost there. I also know that this thing, because I've sampled the signal, will be periodic. It will repeat and repeat and repeat. And so I can immediately just figure out what the rest of the spectrum is going to look like. I'll have an impulse there, 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 I'll have impulses da-da-da-da-da, and I'll have impulses da-da-da-da-da, up to, from minus infinity to infinity. This thing is periodic in its spectrum. Where do these impulses sit? Well, the cool thing is, where does fs land always on the f omega axis? What's the value here? 1. And it's always 1. It's always 1, 2, 3, 4, 5, irrespective of what fs is. Okay, so it's always 1. And that means I can very quickly figure out that this must be 1 minus f0 over fs. This is 1 plus f0 over fs. This is minus 1 plus f0 over fs. This is minus 1 minus f0 over fs. Okay, and it's so cool. I can take any signal that I sample, and I can just immediately see what its discrete time spectrum or discrete time Fourier transform looks like. All I have to do is I just basically divide the axis by fs, okay, and then I repeat periodically. Boom, I've got my spectrum. That's a cool thing about the discrete time Fourier transform. And it will be useful when we get to the DFT. Okay, let's talk about this cycles per sample thing. Let's say in the test I actually give you this signal here, okay? I give you these dots, okay? Okay, it's a sampled cosine, okay? I will quickly write down I will show you how quickly I can draw its spectrum without knowing the sampling frequency, without knowing anything. I'll draw out its spectrum in 3 seconds, okay? Or 4 seconds. This thing's spectrum looks like this. This is x f omega of this thing. I haven't told you the sample frequency. This is in terms of f omega. I know it's a cosine, so I know it's got an impulse and an impulse. I also know that those impulses will repeat, at 1 and at -1. Sorry, this is much longer than 3 seconds, but it's because I'm a slow drawer. Okay, so -1 and at 1. Okay, where does that point sit? I'll show you how quickly I do this. I know that this discrete time frequency thing is continuous cycles per sample. So where's that point? Let me show you. Just approximately. Here's one cycle. This is one cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9-ish. 1/9. -1/9. Okay, and that point there would be, what's this, 8/9. This is 11/9. Okay, you see what I did? This just comes from the units, from the unit manipulation that we did before. I basically saw continuous cycles. There's one continuous cycles. How many samples did it take? 1, 2, 3, 4, 5, 6, 7, 8, 9-ish. Okay, there should be an approximation sign here. It's definitely not exact. So it's cool, and I could draw the spectrum without knowing the sampling frequency or anything else. I just counted cycles per sample. Let's look at the case where that thing is actually exact. We'll do this. So what we're going to do is we're going to look at the periodicity of sampled exponentials. When is a signal periodic in the discrete time domain? Okay, and what we'll do is we'll look at our friend complex exponential, because a complex exponential basically, if we can figure something out for the complex exponential, then we figured it out for all periodic signals. So let's say we've got a sampled complex exponential signal with an amplitude A, it's e to the j 2 pi f omega 0 n plus some phase shift. So this is a very general case, right? It has an amplitude and a phase shift, and it's rotating at a specific frequency. For this thing to be periodic with a period of capital N, it means that everywhere where there's an n, if I substitute in n plus capital N, then it should be equal. Okay, so A, E, J, 2 pi f omega 0 n plus 2 pi f omega 0 capital N plus the phase shift. This should be equal for this thing to be periodic with a period of n. Okay. Now for that to be true, for this to be true, what can you tell me about that thing? 2 pi f omega n. What can you tell me about that? So this thing is a rotating phasor. It rotates, okay? And then this thing is a rotating phasor that rotates on for a little while. For those two to end at the same point, how much should I have rotated into the future? 2 pi is one correct answer. I can also rotate 4 pi and 6 pi and so on. So you've rotated, and then I've rotated, and then I just rotate another 2 pi, 4 pi, 6 pi. So this is true if, this monstrosity is true if this thing is some multiple of 2 pi. So if that's equal to 2 pi k. Okay? And now let's just cancel out stuff here. 2 pi, 2 pi, 2 pi, 2 pi. And what we end up with is that f omega 0 is equal to k over n. We know the units for this thing. It's continuous cycles per sample. The units for n is samples. So that means that k is continuous cycles. This thing, right, you remember from the definition, this is also equal to f0 over fs. Okay, so this is the frequency of the continuous signal, and this is how I sampled it. Okay, just pay attention here. I'm going to say something that should be earth-shattering to you. Not really, but a little bit. I have a periodic signal in the time domain. I have a periodic signal in the time domain. Tung, tung, tung. I sample it. The resulting signal, the resulting sampled signal, doesn't necessarily have to be periodic. Okay, I'll just say that again. I've got a signal in the time domain. It goes like this. I sample it. The resulting signal doesn't necessarily have to be periodic. It is periodic only if f0 divided by fs can be expressed as some integer divided by some integer. So only if f0 divided by fs is some like rational fraction, then the sampled signal is periodic. Otherwise, it's not. Okay, and it doesn't repeat ever again, which is pretty weird. It just means that what's going to happen is you're going to sample, but you're just going to be slightly off. And actually, this sequence here will never repeat again, even though the signal was sampled. So I'll just repeat that. Only if f0 divided by fs, the original frequency of the signal, divided by the sampling frequency, if that is rational, then I get an output signal, a discrete output signal, which is actually periodic. So here is a signal. I ask you very, very quickly, write out an equation for the signal. Write out an equation for the sampled signal. So I have some sinusoid pulsing at 300 hertz, and I sample it at 2000 hertz. Very quickly write out x of n. Okay? And I can do this super quick. I know that f omega 0 is equal to f0, the original frequency of my signal, divided by fs. So that's equal to 300 divided by 2000. So I know that this is 3 over 20. That's the kind of the simplest version of that. So xn, I can just immediately write it down, is equal to sine 2 pi 3 over 20 n. Boom. Okay, and that's without the picture. This 3 over 20, let's just go back here. 3 over 20, it's the most simple form in which I could write f0 over fs, is 3 over 20. What does this tell me? The 3 over 20 tells me that in 20 samples, I will have 3 cycles, continuous cycles, and only then does my signal actually start to repeat. My discrete signal start to repeat. I'll say that again. In 20 samples, I will have 3 continuous cycles, and only then will my signal start to repeat. Okay, so let's check this out. So here's my sine wave. Tunk, 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 tunk. Look at the dots. Okay? Can you tell me where the dot starts to repeat? Yes?
On the fourth peak.
Fourth peak. So here, you're right. So this is actually this is the first point where it repeats, and then there, and then there, and then there, and then there. Spot on. How many continuous cycles do I have before it starts repeating? 3. 1, 2, 3. How many samples do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then it starts to repeat. Okay, I showed off there. I could count to 20 in English. Okay, so I could have actually, in the test, I could have written a different question. I could have not given you this. I could have given you that picture and then asked, write an expression for xn just immediately. And what you would have done is, you would have done what Melvin did. You would check, where the fudge does this thing start to repeat? Oh, it starts to repeat here. Okay. How many continuous cycles do I have before it starts to repeat? 1, 2, 3. How many samples do I have in that time? 20. So it's 3 over 20, and then the rest would fall out. 2 pi n. It's a sine wave because it starts at 0. Sine. Okay, so super easy for a very complicated signal. Okay. If I'm just a little bit off with my sampling frequency, if this fraction can't be put in a rational form with an integer on top of an integer, then what will happen is this sample would just be a little bit off from the one here. And this one would just be a little bit off. And that one would just be a little bit off. And that means that actually, even though we started with a real periodic continuous time signal, when we sampled it, it wasn't periodic anymore.